All right, let's check out this concept of logarithmic functions. And in looking at them, we'll also look at their graphs. You may recall that in our last section, we solved equations of simple exponential functions. Something like 2 to the x equals 8. Now this is very simple, but the concept is profound. And that is, we try to get both sides of the equation with the same base. 2 to the x, 8 to the first. If I can change 8 to 2 to some power, then I have a step up in the advantage category. And as you know, 8 is the same as 2 to the third. So in the place of 8, I'm going to put 2 to the third. Then the observation we made was, hey look, the bases are the same. That means the exponents must be equivalent. So we solved the equation by substituting for 8, 2 to some power, so that there'd be the same base on both sides. All right, consider this. What if we had 2 to the x equals 9? Well, can I express 9 as 2 to some power? 2 to the third is 8, 2 to the fourth is 16, so no, I can't. All I know is basically that whatever this exponent is, it's somewhere above 3 and below 4. Because 3, 2 to the third takes me to 8, 2 to the fourth takes me to 16. How do I get to 9? Well, it's 2 to some power, but it's somewhere between 3 and 4. This is where I realize I need a new concept. A concept called logarithmic functions. Now the interesting thing about logarithmic functions is they are the inverses of the exponential function. Now I'm hoping you remember that once I have a picture of an exponential function, a picture of any function, I can find its inverse by reflecting it over this line, x equal y. This line that goes 45-degree angle right through the origin. Just imagine folding it over that, and we will get this graph right here. So this is the graph of my logarithmic function. Exponential function, y equals 3 to the x. Logarithmic function, its inverse. Well, how do I come up with the expression of the inverse of a function? I think you remember this too. We had some very specific steps for coming up with the inverse of a function. Let's look at this inverse of the function f of x equals 3 to the x. First step was to express the function in y equals form. So instead of f of x equals 3x, y equals 3 to the x. All right, that's step 1. Step 2 is to interchange the x and the y. So now I get x is 3 to the y power. Step 3 is where I run into some problems. Step 3 says solve that equation for y. All I can basically say is I can in solving this for y, I can make a statement about y. I can say this: y is the exponent I raise 3 to in order to get x. Y is the exponent that I raise 3 to in order to get x. Well, this is actually a statement of the logarithmic function. And here's what we're going to do. The exponent that I raise 3 to, we're going to express as log base 3. So the exponent that I raise 3 to, we're going to express as log base 3. So the exponent that I raise 3 to in order to get x is y. The exponent that I raise 3 to in order to get x is y. So this is a re-expression of 3 to the y power is x. 3 to the y power is x. So another way to say this, and by the way, many of your problems are going to ask you to change a logarithmic expression to an exponential expression. And here's how you do it. 3 to the y is x. Well, that was easy. Base, base. Another way to read this is log base 3. And the exponent is the log. Log base 3 of x is y. Another way to say that, 3 to the y power is x. Let's look at a couple more illustrations. Like 10 to the third power is 1,000. Can you express that in logarithmic terms? Well, log base, hey, this is the base, so same base. Log base 10 of 1,000 is 3. Another way to say it, the exponent that I raise 10 to in order to get 1,000 is 3. The exponent that I raise 10 to in order to get 1,000 is 3. Base, base. How about this one? Can you put this in logarithmic terms? And keep in mind the base is going to be the base of your log. So log base 2, that's the base. The exponent that I raise 2 to in order to get 32 is 5. 2 to the 5th power is 32. Well, how about if we're going the other way? Log base 5 of 125 is 3. Can you express that in exponential form? And one thing you're going to discover in solving some of our problems is it's not going to be solvable in logarithmic form, but if I express it in exponential form, I can see what to do. Base, base. 5 to the third power is 125. So if you just have a couple of examples like this handy, you're going to be able to move easily from an exponential to logarithmic or logarithmic to exponential expression. All right, some of you guys know that you rarely see an expression like this, log base 10. And here's why. I have a couple of very familiar, frequently encountered logs, and they look like this. most frequently encountered logs. The first is log base 10. This is called the common log. And you probably guess why it's called the common log. It appears commonly, often. And on your calculator, it is designated log. The function key on your calculator is log. So when you see log base 10, you're more frequently going to see it simply expressed as log. Log base 10 is simply expressed as log. So if you see log of 100, another way to think of that is log base 10 of 100. The exponent that I raised 10 to in order to get 100 is going to be 2. And you're going to have to figure out how to use your particular calculator. In my particular calculator, I have to enter this number before I hit the log function key. Like if I want to find the log base 10 of 100, I submit 100, hit the log key, and it tells me it's 2. But you're going to have to make sure yours works, or in which order yours works. All right, this is the common log. There is another frequently encountered log, and that is log base e. And that is called the natural log. It's called the natural log because this number e, that's an irrational number just like pi. This number e shows up almost universally in any function that deals with natural growth or decline that you see in bacteria, in populations, in plant expansion. If you want to know how bacteria is growing in a petri dish, the function that's going to determine that will have an e in it. If you want to see how a population is increasing or decreasing in a particular society, the function that involves that will have this number e involved. And log base e is expressed on your calculator as ln. So when you see ln on your calculator, you got yourself the natural log. Here's ln right there. All right, so these two guys show up often. The common log is just log, that means log base 10. The natural log is indicated ln, that means log base e. And by the way, let's see. Oops. All right, so there are a couple of common expressions in logarithms that you're going to want to be familiar with. Now, you guys are familiar with this concept that any number to the 0 power is going to give you what? 1. Any number to the 0 power is going to give you 1, right? So if I were to put that in logarithmic form, it would look like this. The exponent that I raise x to in order to get 1 is 0. So in other words, log base anything of 1 is 0. And I can write it in general. Log base anything of 1 is going to be 0. You're also familiar with this concept, that any number to the first power is just going to be itself, right? Now, if I put that in logarithmic form, it would be log base x, log base x of x is 1. The exponent that I raise x to in order to get x is 1. So what I can write in general is log base a, any number, of a is going to be 1. So if I have, for instance, log base 17 of 1, what's that going to give me? Hey, log base anything of 1 is going to be 0. How about if I had log base 9 of 9? What would that give me? Log base anything of itself is going to be 1. So these three concepts, oh, that means I need one more. Here's the third one. Log base a of a to the x is just going to be x. Example, log base 5 of 5 to the 4th is going to be 4. Think about it. The exponent that I raise 5 to in order to get 5 to the 4th, is 4. So these three we're going to be referring to as we work our problems along the way. So I'll keep this sheet handy. All right, let's work some problems. Identify the graph for h of x equals log base 9 of x minus 1. Now, there's a couple of different ways you can do this. What I suggest you do is find, you know how Hawk says this, he's going to give you 4 graphs and you got to pick the one, right? So if I can find 2 points on this graph, then I can find which of the 4 graphs identifies with this guy. So I'm going to find 2 illustrative points. So I'm going to call this y equals. I'm going to put it in y equals form because I need to find an x and a y to find a point, right? So log base 9 of x minus 1. Now, a couple of things that I should remind you of come from this list right here. Log base 9 of 1 is going to be 0. Log base 9 of 1, log base anything of 1 is going to be 0. Something else I should remind you of is that log base 9 of 9 is going to be 1. I'm going to keep these concepts at my fingertips here. Log base 9 of 9 is going to be 1. So if I can get this thing in parentheses to be 1, and I can get this thing in parentheses to be 9, then I know the answer to my question. So here's my grid. Now here's the question. What would I have to pick for x to make this log base 9 of 1? What would x have to be in order to make these parentheses 1? Well, obviously 2 minus 1 is 1, so I'm going to pick 2 for my x. Log base 9 of 2 minus 1 is log base 9 of 1. Log base 9 of 1 is going to be 0. See what we had to do? We had to figure out what does x have to be to arrive to this configuration? All right, second configuration, log base 9 of 9. What does x have to be in order to make this parentheses 9? What minus 1 is 9? Oh yeah, I'm going to choose 10 for x. 10 minus 1 is 9. Log base 9 of 9 is 1. So on my graph, I have the points 2, 0, and 10, 1, 3, 4, 5, 6. Now, all you have to do, hey, what does this graph look like? It's something like this, I'm not sure. But all you have to do is find the graph with these 2 points, and you got it. Find the graph with these 2 points, and you got it. That's all you got to do. All right, onward and upward. Evaluate, it says, without a calculator. Log base, hey, you know what the log base here is? That's right, it's 10. Another way to write this is log base 10 of 10. Hey, wait a minute. Log base a of a, log base anything of itself is going to be 1. Log base anything of itself is going to be 1. Boy, that was fast. Okay, let's try this one. Use properties of logarithms to solve the following equation. Now here's the perfect example of a logarithmic expression being very vague and hard to grasp. But if I were to express in exponential form, let's see what happens. 2 to the 5th power equals 7x. Right? Base to the exponent equals 7x. Hey, I know what 2 to the 5th power is. I got a little chart. 2 to the 5th power is 32. This is going to be easy. Divide both sides by 7, and I got it. X is 32 over 7. They want me to reduce it if it will. It won't. That's it. Notice this expression, got no idea what to do. Put it in exponential form. Hey, this is easy. 2 to the 5th is just 32. Solve from there. All right, let's identify the graph for, oh yikes. M of x equals 4 minus log base 1/3 of x plus 1. Here's what I suggest we do. Find a couple of illustrative points. Here's one thing I know. Here's 2 things I know. I know that log base 1/3 of 1, log base anything of 1 is 0. So I know that log base 1/3 of 1 is going to be 0. Here's the second thing I know. Log base 1/3 of 1/3, log base anything of itself is going to be 1. Log base 1/3 of 1/3 is going to give me 1. I'm going to use these same 2 concepts to find my 2 illustrative points. All right, the first thing I suggest you do after you say y equals is put this 4 at the end. That way I can look at the log by itself. It's a positive 4, so plus 4. So I'm going to give me 2 points here. And you know, when I'm identifying these graphs, if I can find 2 points, that's all I need to separate the correct one from the 3 incorrect ones. All right, first thing I know is that log base, forget about the negative for just a second, log base 1/3 of 1 is going to give me 0. So what do I have to do to make that in parentheses 1? I want to evaluate log base 1/3 of 1. What would x have to be to make this 1? Why 0. 0 plus 1 is 1. Log base 1/3 of 1 is 0. The negative of 0 is still 0. Plus 4 is 4. Once again, I'll let x be 0. Log base 1/3 of 0 plus 1 is log base 1/3 of 1. And I know that log base anything of 1 is going to be 0. So that gives me negative 0, which is still 0, plus 4 is 4. All right, the next thing I want in parentheses is 1/3, because I know that log base 1/3 of 1/3 is going to be 1. So that would be very easy. But here's a tricky question. What does x have to be to make this 1/3? Some of you can see it. It's going to be, by the way, negative 2/3. But let's say you can't see it. So what I do is I take x plus 1, and I want it to end up to be 1/3. So I'm going to have to subtract 1 from both sides. X is 1/3 minus 1, which is 3/3. X is negative 2/3. So I'm going to pick negative 2/3. Seems kind of weird, but I want it to end up really nice and neat. I'm going to pick negative 2/3 for my x. Here we go. Negative 2/3 plus 1 is 1/3. Log base 1/3 of 1/3 is 1. Negative of 1 is negative 1. Negative 1 plus 4 is 3. Got my 2 points. Plot these 2 points, 0, 4. And negative 2/3, 3. Negative 2/3, 1, 2, 3. And find the graph. Find the graph that has these 2 points in it, and you got it. It's going to be that simple. All right, next one. Solve the following equation. Hey, this looks familiar. If I re-express natural log as log base e of e to the x equal 22.7. I want you to look here. Log base e of e to some power equals that power. Or another way you could think of it, let's put this in exponential form. What that means is e to the 22.7 equals e to the x. That to that equals that. That's how you put it in exponential form. Hey, look here, same base. That means that my 2 exponents must be equivalent. X is 22.7. So again, in logarithmic form, it's confusing. Put it in exponential form, it begins to make a little bit more sense. Okay, one more graph. Identify the graph of log base 6 of x plus 2. Now, let's go over again 2 things I know for sure about log base 6? I know that log base 6 of 1 is going to be 0. And I know that log base 6 of 6 is going to be 1. So I'm going to be picking 1 and 6 for my x. Let's see what happens. First of all, let's re-express it as y equals log base 6 of x plus 2. For my x, I'm going to pick 1. Log base 6 of 1. Log base anything of 1 is 0. So log base 6 of 1 is going to be 0. 0 plus 2 is going to give me 2. Now I'm going to pick 6 for my x because I also want to evaluate log base 6 of 6. Do the ones that are easy. So x is 6. Log base 6 of 6 is... Log base 6 of 6 is 1. 1 plus 2 is 3. So I'm going to look for the graph that has the points 1, 2, and 6, 3. Whatever that graph looks like, it's going to have those 2 points, 1, 2, and 6, 3. All right, not too bad, huh? Next one says evaluate without using a calculator. Well, let's think about this for a minute. This is ln, the natural log. Let's rewrite it as log base e, the 6th root of e squared. Do you remember when we talked about rational exponents? We looked at the concept of 8 to the 2/3 power. That basically means the cube root of 8 squared. That the denominator is the index, the numerator is the exponent. So can you look at this, that it's the same as that, and change this expression to e to some fractional exponent? Remember, the index is going to be your denominator. So 2 over 6. That equals log base e of e to the 1/3. Remember this third concept. Log base anything of anything to a power is that power. Log base e of e to a power is that power. Log base e of e to the 1/3, why, that's just 1/3. And that's your third property, or third familiar expression of logarithmic form. So think of natural log as log base e. Re-express the radical expression as a fractional exponent. Simplify it. And what do you know? I have the same base as this base. Log base e of e to a power is the power. All right, use properties of logarithms to solve the following. Log base, this is confusing. Let's re-express as, put it in exponential form. Now this is basically the skill step that is going to allow you to move from this to a more convenient form. What to what power equals what? Here we go. The base So that's going to be the base here. This is my exponent. So all I have to do is evaluate 128 to the 2/7 power. And by the way, you can do this with a calculator. 128 do to the power of, and in parentheses do 2 divided 7 equals, and you'll get your answer. But let's use the translation of a fractional exponent to a radical expression. 128 to the 2/7 means the 7th root of 128 squared. Now my chart for 2 just goes up to 2 to the 6th, but 2 to the 7th is going to be 128. So 2 to the 7th power. So another way to say, or the 7th root of 128 is 2. And you can also do this with your calculator, the 7th root of 128. Then the number that I can multiply by itself 7 times and end up with 128 is 2. And 2 squared, x is going to be 4. So I would suggest calculator either here or here. This is not easy stuff. Solve the following equation. Again, it's a logarithmic expression. Let's put it in exponential form and see what it looks like. Hey, exponential form may not help us, but then again, it may. What to what power? Remember? 8 to the 2nd power is that. Hey, this is going to be easy, because I can do 8 squared, that's 64. That's going to be an easy linear equation to solve. Add 4 to both sides. Divide both sides by 2, and I got it. Again, the logarithmic expression, vague, obtuse, abstract. I don't know what to do here. Put it in exponential form. Hey, that's easy. Solve, it says, use a calculator if you need to. And here they give me an approximation of E. E is approximately 2.7183. All right, let's see what we got here. Again, let's re-express natural log as log base what? E. Remember, log is log base 10. Ln is log base E. All right, I do this so I can express in exponential form. Can't express it in exponential form unless I have a base and make it, I got a base here, but make it visible. What to what power equals what? Here we go. E to the 5th power equals that. Here's where I'm obviously going to need my calculator. So I got to do e to the 5th power. Now I have a function key here. It's a second function. It's e to the x. If you don't have that or can't find it, simply use this. Simply use 2.7183. So I'm going to use my e to the x power, and what I have to do is put in the exponent first. 5, then hit my e to the x power, and I get 148.41315991. Now I don't have to write this down. I can simply use my calculator, because now I'm going to subtract 14 from both sides. Minus 14 equals, and I get 134 point, same thing, Now I'm going to divide both sides by 6. Divide 6 equals, and I get x is 22.402. I think it says 3 decimal places. So x is approximately equal to 22.402. But notice, please, I had to use either my calculator or this approximation for e. I had to change my natural log to log base e and then put it in exponential form. E to the 5th power equals that. It's ugly, but it's solvable. All right, it says evaluate without a calculator. Let's see, log base 1/5 of 25 equals, let's say, x. I don't know. Let's see here. Oh, well, let's put it in exponential form and see if something becomes obvious. What to what power? You see? 1/5 to the x power equals 25. Now this is where I have to get the same base on both sides. You see what that base is going to be? Probably going to be 5. I would suggest 5. 25 is 5 squared. That's easy. But this is 1/5. This is not 5. Hey, you know what I can do? I can move this to the other part of the fraction and change the sign of my exponent. So in the place of 1/5, I express 1/5 as 5 to the negative 1. Power to a power, multiply your exponents. Negative 1 times x. Same base. That means my exponents must be equivalent. Negative x equals 2. Divide both sides by negative 1, or multiply both sides by negative 1. X is negative 2. So again, re-express in exponential form, and then find a common base so that you can make the exponents equivalent. One more to go. Write as an exponential equation. All they want me to do is write this as an exponential equation. Now we usually have it the other way, so let me write it the other way, just so it looks more familiar. Log base 4.4 of v equals 4. All right, put it in exponential form. What to what power equals what? That's the base. 4.4 to the 4th power equals v. And that's it. They don't want me to solve anything. They just want me to write it in exponential form, and that's all I have to do. All right, challenging section. Good luck as you work through your problems.